Good morning, everyone. Welcome back to class. We're going to pick back up in chapter 4 from where we left off on Friday. We're talking about solutions and how we can prepare and talk about concentrations of solutions and that are ionic compounds like KNO3. When something like this compound dissolves in water, it's really ionizing the K plus and nitrate ion. And we get the ionization process. And so then if we recall, the opening demo we did in the class, we saw a light bulb being lit up due to the presence of these ions in solution. So ions in solution, those act as electrolytes. They kind of act as a wire to bridge the electrodes of that light bulb so we can light the light bulb up. And so the nature of being an electrolyte is the formation of these ions. The ions conducting electricity is one of their properties. And so conductivity is generally proportional to the total concentration of ions dissolved in a solution. So if we can have more ions dissolved into a particular solution, it should be more conductive. So we put a mole of each of these compounds below into 10 liters of water. Which one should have the greatest conductivity? Well, KNO3 gives us 2 moles of ions in that solution. And then we have that, over the 10 liters. So if we're thinking of our ion concentration, it would be, 2 divided by 10. KClO3, again, we might get a little bit confused sometimes. Sometimes we might think this goes to K plus, Cl minus, and O2 minus. This actually just goes to K plus and ClO3 minus. We have to be able to recognize that chlorate ion, and that ion stays intact in solution. So we also get 2 moles of ions with KClO3. It has the exact same ion concentration. Calcium hydroxide, this, you might be thinking here, is this an AQ or is this a solid? Is this water soluble? It is water soluble, meaning we might think about double checking our solubility chart, and this is water soluble. And so this would be calcium ion and 2 hydroxide ions. That would give us 3 moles of ions in this solution, in that 10 liter solution. Because we're imagining taking a mole of the compound and dissolving that into 10 liters of water. And so then we do this with AlCl3. Again, most chlorides are water soluble. We have 3 exceptions, of which aluminum's not. So this is definitely water soluble. So in solution, this is aluminum 3 plus and 3 Cl minus. So that gives us 4 moles of ions. And so, of course, that one's going to lead to the highest ion concentration. So here we're going to have 4 over 10 instead of 2 over 10 or 3 over 10. And so compound D gives us the highest ion concentration in the solution and hence the greatest conductivity. So conductivity is increasing due to the presence of these electrolytes in the solution. Okay, so we can take solutions and change their concentrations. Primarily, we do this through dilution. You can imagine evaporating a solvent. You could take most of your ionic compounds. They have really high melting points and boiling points. So if you heat up, in fact, we talked about a sodium chloride solution back in chapter 1, where we could distill the mixture. You might remember we could pull some of the water off the mixture, leaving behind the sodium chloride. So you can imagine the opposite of dilution would be increasing the concentration through like boiling off the water. But primarily, we just usually talk about dilution, where you can imagine taking a solution and then taking a portion of it, maybe with a pipette, delivering that into a new volumetric piece of glassware, and then adding water to change the concentration. So here we're going from a high concentration of some solution to then a lower concentration. So we can dilute through just adding water. Now, in the particular example, let me zoom in a little bit here. They're specifically taking 25.0 milliliters of some 1.00 mole per liter solution. This is probably copper, because copper 2 plus is blue, so I'm guessing this is probably like copper nitrate or something like that. But it doesn't quite matter what the compound is. It just matters that it's 1.00 moles per liter in our original solution. And we took 25 milliliters of that solution and placed it into a 250 milliliter piece of glassware. This glassware, if you didn't realize, it has a little marking on it. You can see the marking here. You can probably barely make out that marking there. That's designed, you can fill with water, to the meniscus of water to that particular point. And then that piece of glassware would be holding about 250.0 milliliters. And so this is just a way of adding water to know the total volume of that solution once we've added that new water. Now, these problems could get a little tricky where depending on the concentrations of the solution and the nature of the compounds involved, it might not have been exactly 225.0 milliliters of water needed to be added to the 25 mils of solution. So a lot of times in these problems, you're told that you add enough water to reach the calibration mark on the neck of the flask, which in this case would be 250.0 milliliters, and this is then the total volume of that new solution. Because for molarity, often what we want to know is what's the moles of the solute in the solution divided by the total volume of the solution. And so a few ways we can think about the math here would be, well, how many moles did we start with here? We took 25 mils of 1.00 molar solution. So let's do that up here. If we have 1.00 mole, let's just call it X, so we can think of moles of something per liter. And we took 0.0250 liters of that solution by withdrawing that 25 mil pipette portion. And so it cancels out our volume unit. So we have 0.0250 moles of Twitter, I don't know. So moles of X. And so then when we change the total volume of the solution, we haven't changed the moles of the solute. Like that's the key. Is like by adding water, you're not changing the moles of solute. We're just changing the total volume. And so the new concentration of X, once we dilute it, would just be equal to 0.0250 moles of X that was in that initial portion we withdrew. And then we change this to a total volume of 0.250 liters. And technically, I think an extra zero for thinking sig figs. We probably get 250.0 milliliters. But we have 3 divided by 4 sig figs. And then also with molarity, it's almost always moles per liter. So that's why I'm converting the volume unit to liters here. And so this should work out to be 0.100 mole per liter. And then mole per liter, so moles of X per liter, that's synonymous with saying 0.100 M of whatever that compound is. So if we started with 1.00 mole per liter of whatever this compound is, we ended up with 0.100 mole per liter of whatever that compound is through this dilution step. And so that's how we can do a dilution, is just by thinking that we're not changing the moles of solute, that the moles of the solute are staying constant because we're only adding solvent to the mixture. And so let's look at another problem. I'll even introduce a different equation here. Let's actually start setting this problem up here together, where we have so much calcium hydroxide mixed with water to yield a 1 liter solution. And then we're going to take 10 mils of that solution and then mix it with another portion of water and then ask the concentration of that final solution in units of molarity, moles per liter. Okay, so let's think of the first dilution step. We're taking so much of this compound and preparing a 1 liter solution. So our concentration of calcium hydroxide, maybe we'll call this the initial solution, because we're going to change it in the second step. Let's calculate this initial concentration. .0 grams of calcium hydroxide. This is the molar mass. This is often the way in like an exam problem will give you a molar mass. So 74.08 grams per mole of calcium hydroxide. So molarity, this is concentration or molarity of what's inside of the bracket. So the concentration of calcium hydroxide is the moles of calcium hydroxide, and then divide by the volume of that solution. It's 1.00 liters. So that concentration, 25 divided by 74.08 divided by 1 is 0.337 moles per liter. Now I can write M, that's just moles per liter. So whenever I see this M, I might be thinking, okay, this is just moles per liter. Moles of the calcium hydroxide per liter of that solution. Now let me derive an equation. Now, sometimes equations are good, sometimes they're bad. They're, I think, bad when we don't know where they come from and just blindly apply them to a problem, but they're good when we understand why an equation might make sense. If I take a molarity, like such as this molarity here, a moles per liter, and if I multiply it by a volume, then I would get moles, right? So I could write that the moles of my initial solution, like the moles in this initial solution where I have a liter of it, I could calculate that initial moles by taking this initial molarity that we just calculated and then multiplying by the initial volume. Now, what I might then think is the initial volume might be where I take 10 mils of that solution. So I'm going to take 10 milliliters of this solution that I just prepared. So we just prepared a liter. I'm going to take 10 milliliters of it. So I might be thinking this is my 10 milliliters here. And then this initial molarity might be my 0.337 moles per liter that we just calculated. So if I multiply those two units together, maybe if I convert milliliters to liters as well, but we'll talk about that in a minute, but we would get moles that are initially present inside of that solution. And then if we think we do a dilution step, so we add water, so we're going to add enough water to go to, or we're adding specifically 75 mils of water, presumably we're going to end with a total volume of 85 milliliters. And so if I take my final volume and multiply it by the final molarity, that should give me the number of moles that are present in that solution. Okay, so if I take the final molarity, which I don't know yet, and I know this should be about the initial 10 milliliters and then plus the 75.0 milliliters of water that I just added to give me 85.0 milliliters of total solution. So my total volume is 85 mils. Well, my final number of moles of that solute shouldn't be changing, right? So the final number of moles here should be equal to the initial number of moles, since we're just diluting. So the final number of moles really isn't changing because we're just adding water here. We're not changing the total moles of solute. And so this should be equal to Ni. And if Ni is equal to MiVi, then MFVF should be equal to MiVi. So we end up with like this expression here that if you're following the logic, it's just saying if I know the initial molarity, initial volume, I can multiply them together, gives me the initial moles. Then if I take the final molarity, final volume, multiply them together, that also gives me the initial moles, which then sets them equal to each other. So we get this expression MiVi equals MFVF. Sometimes it's called M1V1 equals M2V2, where I think the ones and twos is a little bit misleading, sometimes might lead you to using that equation in other problems that aren't dilution problems. So this is a dilution equation and should work whenever we're doing a dilution step. So whenever we're doing an actual dilution is where we're just adding water, changing the concentration of a solution, then this equation should apply. It could be a useful equation that we can use. And so I think you can see here, now the reason why I didn't worry about converting my volume units is I can actually leave the volumes in milliliters here if I want, as long as both volumes are in the same unit. So we can leave VI as 10 mils and VF as 85 mils, as long as they're both in milliliters. Or if we want to convert one to liters, we just have to convert the other to liters. And so let me rewrite MiVi equals MFVF down here. And then I can solve for the final molarity by MiVi divided by VF. And my initial molarity was 0.337 moles per liter times 10 milliliters. 10 mils because we just took 10 mils of that solution. And then we're dividing that by 85.0 milliliters. So if I go 0.337 times 10, divide by 85, should go down, and it does, to 0.0397. Moles of calcium hydroxide per liter of that solution. Now, what else could we have done? This isn't the only way to solve the problem, or even the use of this equation is useful if we understand the equation, if we can know when it applies. But another way we could have solved the problem would have just been to go back to what molarity is. We could have just said, well, I could take the 10 milliliters, convert it to liters, right? And I could multiply this by the moles per liter. So another approach would have been just to say, well, I can calculate the moles of calcium hydroxide in that 10 ml solution. It would be 0.0337 moles. And then I can also then say that the new and final molarity, or let me just write that as the final molarity of the solution, should just be that number of moles divided by the new volume. So just 85 mils, but expressed in liters. So it's actually not even that hard. It's somewhat fewer steps and even less thinking maybe not to even use the equation, just to use the concept of what molarity is. Just making sure this works. Oh, yeah, this is 0.0037. So 0.01 times 0.337 is 0.0037. Divide that by 0.085, gives us the right answer. So really the main message is just using a molarity. Molarity times the volume is moles. I can see that in equation form perhaps, or I can just see that through dimensional analysis. Dimensional analysis is great because we're just plugging in units. One recommendation I would have is anytime you see like a capital M in a problem, if you're always processing that as moles per liter, moles of whatever the compound is per liter, and when you're writing out a step, if you need to do dimensional analysis, let's write out explicitly moles per liter. That helps us make sure that we're multiplying by volume and not making a mistake like dividing by volume. And so we multiply by volume here to cancel out liters, and then we divide by volume here to go back to moles per liter. So the final section in the chapter, we do have to circle back still after this is section 4.4, so we skipped a section in the middle. But the last section in chapter 4 is on solution stoichiometry. And a lot of these problems actually will look and are very similar to the problems we solved in chapter 3. So the idea in chapter 3 was that if we gave you the mass of a reactant, we're just picturing maybe like A goes to 2B or something like that. So just imagining some reaction. So if I give you the mass of A, then you can use the molar mass of A to convert to moles. I think we're all sick. This is going to be an interesting week or two, I think. I'll get that for you. The analogy to the football game is like when you're at a test and you can't figure out that last problem, and like they're like, all right, you have 30 seconds to go, and then you're like, oh yeah, there it is. And you pull out the exam and you get the good grade. All right. There's a lot of analogies to football actually, or even sports, like the sports team didn't stay up Friday night studying for the game, right? Or maybe they did, I don't know. Okay, anyways, back to the thought here. So again, chapter 3 had us going through mass of A, molar mass of A, converting to moles of A, and then we can convert to moles of B using the coefficients in the reaction. So if I give you 5 grams of A, you can convert to moles of A if you know the molar mass, and then you can figure out for every mole of A, you need 2 moles of B to form. Molar mass of B would get you the mass of B. Well, here in chapter 4, the only difference is you can use molarity and volume to get the moles. So we can give you molarity of A or B. You can use molarity and the volume to get to the moles of one of the reactants. And then you can use the coefficients to relate the moles of A and B, just like in chapter 3, and then use molarity to get back to volume. So let's look at such a problem where we just introduce the molarity unit within the stoichiometry problem. So we come back to a calcium hydroxide example. So how many grams of calcium hydroxide must be added to completely neutralize, that means to fully react with 25 mils of 0.75 molar nitric acid. Now, they gave us the reaction here, but I want us to think for a minute that we have a base here, one of our strong bases, water-soluble compound containing hydroxide, and we have an acid, and that an acid and a base should react together to form a salt plus water. So that the reaction of a acid and a base together should be a salt plus water. Now, they give us the reaction of the acid plus base goes to the salt plus water. They even balance it for us. But I just want us to recall that we can write and predict the product of this reaction. We can predict the physical state being aqueous because calcium nitrate's water soluble, water liquid because we're forming more of the solvent, and then starting with aqueous substances, water soluble. So we could write and balance this reaction if we needed to, given this type of problem. Now, what they gave us here is information that we could use to calculate the moles of nitric acid. And for every 2 moles of nitric acid, we need to have 1 mole of calcium hydroxide present to fully react with it. So how much mass of calcium hydroxide can react with a given amount of nitric acid? We could set up a BCA chart. I really don't want to go there, but if we wanted to set a BCA chart up, I'm probably just calculating the before moles of nitric acid initially, not sure how much calcium hydroxide we have, and then it's a minus 2x minus x. If we want to use dimensional analysis to solve this problem, I probably just start it this way here. I say how many grams of calcium hydroxide are needed to fully react with this amount of nitric acid. I might start with the 0.750. And again, this is really useful if we go M as mole HNO3 per liter of that solution. Helps us see that we're multiplying by the volume. And it's per liter, so we go 0.0250 liters to cancel out. And then that would give us, if we stopped and calculated the moles of nitric acid present, and then we just want to use the coefficients in the reaction. For every 2 moles of HNO3, we need to add 1 mole of calcium hydroxide to react with it. And then we want to know the mass. We could have said how many milliliters of a 1 molar solution or whatever. That'd be one variation of this problem, but the other variation is just to kind of make it like a chapter 3 question. How many grams do we need to add? And then we just use a molar mass. And so we just multiply by the grams per mole. So being very clear with our units makes this problem, I think, pretty easy to avoid a mistake. The easiest way to make a mistake is if we don't write in our units, maybe we're multiplying by 2 here instead of dividing by 2. But let me give you guys a minute to calculate this out or just catch up on anything with your neighbors if you want to just take a minute or 2 to solve this problem and kind of catch up to where we're at. Okay, well this ends up working out to be answer A. And hopefully you're all just seeing the analogy to chapter 3, and that this is just introducing using the molarity unit along with a volume. Now there's a sort of second section to this final topic, which is on doing things like titrations or doing some analysis with solution stoichiometry. And I wanted to mention that we're not going to cover this particular topic on exams. You do this in a lab. And so we'll just go through this kind of in a picture diagram. And you've probably already done this in the lab. But you could take, or imagine taking a volume of an acid where you don't know the concentration, and you can maybe add that solution to an Erlenmeyer flask. You add what's really necessary, some sort of acid-base indicator, something that might be one color in an acidic solution. And then if we're going to dropwise add base until we get to the situation where we have an excess of base, well, if that indicator changes color in excess base, and we can mark the point where we precisely added the right amount of base to fully react with the acid. And so you actually talk about indicators in chapters, I think it's 16 in the book or 17, where you actually talk a little bit about the nature of indicators. It's just really, they change, their acid versus base behavior at the same pH or the same acid or base conditions that the solution's changing, and undergo a color change. And so that's a very important color change for us to see. So then we add what's known as like a standard solution, a solution we already know the concentration. So you start with sodium hydroxide where you know its concentration, you add it dropwise, or you add it slowly so you can figure out the precise volume needed to exactly reach the point of that color change, called the endpoint. And then from the volume and the concentration of that sodium hydroxide solution, you can then work out what the concentration that acid solution had to be. So this is a lab technique for determining concentrations of unknown solutions so that you can work those out. And it's, we could go into a lot of detail here, but we're not going to since we're not covering this on exams, and you do this enough in the lab. One interesting thing that you do in the lab is you actually start with a solid organic acid that you can actually put in the oven, dry out, so you can have a acid that's in solid form that you can weigh out and precisely get the moles of the acid just by weighing out the sample. And then that's like the first thing that you probably titrated. I'm guessing it was potassium hydrogen phthalate. That's usually what we use, is that compound to start with. And so then that's how you end up getting your standard solution. So you use an acid like that to standardize your base, then you standardize the base, titrate some other solution, get its concentration. Okay, so I just wanted to mention that these topics here, you might see them. I like to I think it's good to know what kind of questions might you see on some old exams, and primarily these daily quizzes. And this is a weird moment where I'm not entirely sure we're going to even stick with these topics being removed from exams, because if we next year decide to throw them back on. But you're going to see a couple of problems on exams that relate to a titration problem. So anytime you're given a concentration of something and asked to determine the concentration of something else through like a titration type problem, that's not something you need to worry about studying for midterm 2. So determining unknown concentrations wouldn't be on midterm 2. Determining a molecular weight of some sort of compound through a titration analysis also wouldn't be covered. And then determining like compositions of mixtures. There's some problems that are like, oh, you take a compound, dissolve it, and precipitate it, and from the precipitate mass, you can work out some percent by mass. So just know the main problems to prepare for are just basic stoichiometry problems from chapter 4, meaning how much of one reactant reacts with another. And then there's one other variation of a problem. There's one other variation that we'll see on Wednesday in class that relates to calculating like ion concentrations after a reaction takes place. So anything kind of just relating, setting up either a BCA chart or a stoichiometry problem with dimensional analysis, that's what we're thinking about looking for problems to study heading into our next midterm. And so, circling back to section 4.4 to kind of wrap up the topics from chapter 4, get into oxidation reduction reactions. So the first half of the section talks about assigning oxidation numbers. Let me just briefly mention that why we're doing this is so that you can look at a reaction, say that 2H2 plus O2 goes to water, and we can try to determine if this reaction here involves charge transfer or not. We're going to try to determine if this is an oxidation or a reduction reaction. Those reactions generally have to occur in tandem. So the oxidation, I think this is on a later slide, but oxidation is losing electrons in a reaction. Reduction is the opposite, it's gaining electrons. And here, we're going to see that hydrogen and oxygen start off neutral in charge, where the atoms don't have any charge yet on them. and then hydrogen ends up positively charged, oxygen ends up negatively charged. Hydrogen's really not ionic. This is like a bookkeeping system. We're going to see that the main application here is that hydrogen ends up with some partial positive charge, but it's positive. Oxygen ends up with some negative charge, not fully -2, but it ends up somewhere negative. We'll talk about why it's partial or like how partial it is when we get to chapter 8 later in the course. But the idea here of using oxidation numbers, it's going to try to help us pick out in a molecule, are some of the atoms more likely to be positively charged, or some atoms more likely to be negatively charged, and then is the reaction involving charge transfer. Since we're ending up with hydrogens picking up a positive charge, that means that they've lost electrons. So you can say that the H here has undergone a loss of electrons, it's been oxidized. And then the O is picking up those electrons, it's gaining electrons to go to the negative charge, and so oxygen's been reduced in this reaction. So the idea of oxidation numbers is they're going to help us try to assign the charge states for like the H and the O. We're going to see by rule, that's how we could get H was +1, O was -2. So the oxidation rules are going to help us pick out the atoms and what their charges are and the reactants and products so we can determine if a given reaction involves a change of charge. And so our basic rules, atomic ions, their oxidation numbers are just their charge. This is really pretty easy. That something like Cl- would just be -1, Na plus would be +1, Mg2 plus +2. So if you have an atomic ion, the oxidation number is just whatever its charge is. Oxygen has the rule that it's -2, except for the case of peroxides and superoxides, and then also compounds with fluorine. So if we actually look at fluorine real quick, fluorine's -1 in all compounds. And so other compounds will adjust their charge to keep F as minus. So let's kind of go through O and F's rule just real quick with a couple examples. And the next slide has a bunch of examples, but I want to see examples now. I want us to see the variation that what we're saying for oxygen is it's -2. So like if we have Na2O, just like we knew from before, plus for sodium, -2 for O, that's the usual oxidation number for O. If we have H2O, -2 for O is its usual charge, +1 for H to adjust accordingly to add up the charge of a neutral molecule. We should be able to sum up all of its oxidation numbers and get to the charge of the molecule neutral for a neutral molecule. Hydrogen's +1 in molecular compounds, -1 in ionic compounds. So anytime I have H paired up with a nonmetal, it's +1. In some rare compounds where it forms a hydride, that's going to be with metal atoms, so an ionic compound. So an example might be CaH2, where you know that calcium is a +2, so hydrogen adjusts accordingly, -2 for the 2, so -1 for each. So that we know from nomenclature would be calcium hydride. And so then let's look at some of the variations of oxygen. Like we already know that peroxide would be something like Na2O2. So for Na2O2, +1 here, +2 overall, gives us an O2 with a -2 overall. And again, from nomenclature, we picked that out as by name sodium peroxide. But now here in chapter 4, what we can see is that the oxidation number per O atom would be that -2 charge for the 2 divided by 2. So just simply -1. So the oxidation number of O, like per one O atom, is -1. There's 2 of them, -2 for the total. So +2, -2 going to neutral for that neutral Na2O, or the Na2O2. We have the superoxide, might be something like KO2. So K plus, of course, O2, for the 2 O's it's -1. So the entire charge of the 2 O's is -1. So per O, it's -0.5. It's not very common you end up with a fractional oxidation number, but here in superoxides, you end up with a fractional oxidation number. Now, not really a stable compound, not that common of an example, so it's not, you're not going to see a lot of things like KO2 where you have this fractional oxidation number, but it just results from the math of the +1 versus the -1 for the entire group of 2 O's. Now let's do a quick example with fluorine. So one compound with fluorine is F2O. Now this here gets into like a pretty useful topic if we can introduce electronegativity. We end up introducing it in chapter 8. Electronegativity, you might have seen this before. It's the desire for electrons in a given atom. The most electronegative atom is fluorine. Fluorine has two good things going for it, or maybe three. One, it has the need for like one more electron. Like neon is already capped off its shell, so neon doesn't really need to capture another electron. Fluorine does, and fluorine really wants another electron because it has a really high positive charge that electrons can experience. We'll talk about that in chapter 7. And then it also is really small. So if you're really small and highly positive, it's really easy to attract a charge towards yourself. If you're a bigger atom, if you're like iodine in that same group, iodine is just so big that it can't pull an electron that close towards itself just due to its larger size. So the smaller a high positive charge is, the better. That's going to be a concept we talk a lot about when we get into chapters 7 and 8. But what that means is fluorine is the one that really wants that electron. It goes negative. It keeps that -1 charge. So fluorine in any compound is -1. And then 2 of them, -2, gives us a +2 for oxygen. So oxygen adjusts its charge, its oxidation number, based off of fluorine staying -1. Now, let's come back to a quick example or a quick analogy that this doesn't mean F2O is ionic. This isn't trying to say F2O is 2 F- ions attached to an O2 plus cation. This is just saying that in a molecule where we know that there should be some shared bonding of, some shared electron pairs. If we're thinking a Lewis structure, there's like shared electrons between the F and the O. That oxygen is just going partial positive. The delta just means partial. The fluorines go partial negative. Where it's not fully -2, but it's negative on F. It's not fully +2 on O, but it's positive. And if you knew the negative charge on F, the charge on O would be 2 times that because there's 2 F's pulling that charge off of the O. And so it's just helping us pick out where the charge is lying on these atoms and these molecules. The more positive charge on O and F2O, the more negative charge on the F. So oxygen's usually -2, exceptions, peroxides, superoxides, and F. Hydrogen +1 in molecular compounds, -1 in ionic. Fluorine's -1 in all compounds. Other halogens are usually -1 unless they're paired up with oxygen or fluorine. So one example could be, and these examples are almost all on the next slide, so maybe we'll skip some of those when we get there, but ClF3, rewrite that. So chlorine trifluoride, the fluorine stays minus. There's 3 of them, -3, so we have a Cl +3. So chlorine's charge in ClF3 would be +3. So it's kind of saying fluorine wants to be the most negative, it stays negative. Oxygen's kind of next. So if we have something like ClO- for hypochlorite, what we'd say here is that the oxygen goes -2 for its ordinary charge. Again, oxygen should be -2 unless it's a peroxide or superoxide. This isn't one of those. Or a compound with F. This doesn't have F, so it goes its ordinary -2. So chlorine has to be +1. +1, so we subtract 2 and get the overall charge of negative for that ClO- ion. So that would be the oxidation numbers of Cl and O in hypochlorite. And then we should be able to deduce other atoms by deduction. So we're just using the idea that we can add up all the oxidation numbers, take into account the formula, and sum up all the oxidation numbers to get the charge of the compound or the ion. So charge of the compound either being neutral if it's a neutral, or whatever the ion is if it's an ion. So another example, NH4+. So we haven't seen nitrogen by rule, but we know hydrogen by rule should be +1 in molecular compounds. And so then we have 4 of them. And then so nitrogen has to be -3. So -3 so that we can add 4 to get to +1 for the overall charge of NH4+. Now, this is maybe so maybe you look at NH4+ and you look at it again, you might think, wait a minute, isn't that an ion? Isn't that an ionic compound? NH4 itself, NH4+ is an ion, but it's not an ionic compound. Like it can form an ionic compound, like NH4Cl is an ionic compound, but NH4+ itself isn't an ionic compound. It's a molecular cation. The bonding within the molecule is molecular. So the bonding between H and N is molecular covalent shared electron bonding. Okay, so we're using that molecular for hydrogen going +1 in molecular compounds. So rules, relatively straightforward, but very nuanced when we start applying these to various examples. So let's look here. Now, one rule we didn't see is just that for a substance that's in its elemental form or hasn't bonded with anything, it has to be 0. So like iron solid, 0. Hydrogen, you have to have compounds. If you just have an element present, the charge of the atom has to be 0. So if you just imagine it this simple, for iron or H2, how could, if one of the irons has a charge, they all have the same charge, and then the substance would have been ionic and not neutral. So if the element's neutral in charge, then all the atoms in the sample have to be neutral in charge. Helium, neutral. Br2, neutral. So anytime you have a neutral molecule, so Br2 was neutral, no charge was indicated, therefore each of the bromine atoms in that sample have to be uncharged or neutral. What about Al2O3? Well, we can actually begin with aluminum or oxygen because we know this is an ionic compound, so the oxidation numbers are just their charges. So aluminum should be +3, oxygen should be -2, and those are from the nature of those atoms, their elements, where they're located on the periodic table, and then also the rule for oxygen that's -2 with its exceptions, and that's not one of the exceptions. So -6 +6. Calcium's a +2, 3 of them +6. 2 nitrogens -6, -3 overall. The name would be calcium nitride. You may recognize that, but that would be calcium nitride, and we could deduce those oxidation numbers. Calcium sulfide, +2, -2. We know calcium's a +2. By default, we can get sulfur's a -2. Sulfur's also in the oxygen group, so -2 makes sense for sulfur. Barium hydride. Barium's in the alkaline group. We know it's a +2. We know that this is an ionic compound. So hydrogen should be -1 in an IC. And +2, -1 makes sense because that sums up to overall neutral. So in some cases, you can know by rule both atoms. So I'd say in this row here, just by the positioning of those atoms on the periodic table and the nature of these being ionic compounds allowed us to know the charge of both atoms. So by default or by definition, we could have gotten both atoms without even needing to deduce the other. O2, F2. Now maybe this gets to a case where we need to think about our rules, where F goes -1 each, 2 of them -2. The 2 O's summed together are +2. So there's 2 of them, so +1 each. So maybe if I make this a little bigger here, again, just to show the thought, -1 for F, -2 for the 2, and then +2 for the O's. There's 2 of them, so +1 per O. So I tried to do the math down here, and I tried to assign the oxidation numbers up top to keep the math separate from the oxidation numbers. KO2, we did this one earlier. This is the plus -0.5. CaO2. Now again, we know calcium's a +2, so then we can deduce that this is the peroxide, the O2 with a -2 overall. -2 divided by 2 is -1 per O. So the oxidation number of O in CaO2 would be -1. Now, if anything, everything's nuanced, right? Until you go through examples and get the distinctions here. Is this a peroxide or superoxide? Because doesn't it look like KO or CaO2? CO2 looks very similar. You might think, okay, this is a peroxide or superoxide. What we have to think here is that peroxides and superoxides, compounds like this, are only forming with certain alkali and alkaline metals. Like the peroxides and the superoxides, very rare compounds. They're not really forming with other elements. You have hydrogen peroxide, but that's about it for peroxide. So this just has to be an ordinary -2. So the peroxides or superoxides exceptions, those are rare compounds, and you're only going to get a peroxide or superoxide when you know the other atom's charge. So you should only be realizing something's a peroxide or superoxide by knowing the other atom's charge to start with. And carbon, we don't know its charge. There's no rule for carbon. So to get carbon here, we have to start with oxygen as being a -2, and then there's 2 of them, -4, so a +4 for carbon. So if you don't know O, like the only way you should get O's charge is by default starting with some other atom in the formula first. And we can't start with C. We don't know C's charge. So that's another way we can know O has to be just the ordinary -2 oxidation number. Now MnO2, again, this is just another distinction that manganese isn't one of those oxide or peroxides. We don't know the charge of manganese in the transition metal row. So I can't start with the charge of manganese, but I can start with oxygen being a -2. So again, this might look like a peroxide or superoxide. You might be a little confused, but just know only the first and second groups of elements can form peroxides and superoxides. And so this has to be an ordinary oxide, -4, manganese +4. What about copper ClO4 Well, this is helpful if we remember charges from chapter 2. ClO4 is a minus. There's 2 of them, -2. That's how we can really quickly work out this is copper +2. So we probably want to remember that ClO4 has a minus charge to help us with this problem. And then once we know ClO4 is a minus, we have kind of 2 choices. I can either work out O and Cl, separately in ClO4 minus, or I can think about the entire compound. Let's kind of think about it both ways. So let's say we know ClO4 is a minus. And so let's work out the charge of O. So O should just be the ordinary -2. There's 4 of them, -8. And then that gives us chlorine +7. So I can subtract 8 to get to the minus charge of that perchlorate ion. So this would be +7 for chlorine. If you were to come back up to the compound here and double check, you're just probably doing a -2 for the O's and then doing times 8 for ClO4 times 2. So you're probably doing a -16 for all of those atoms here, and then we're getting a +14 because we already have the +2 over here. So +2 + 14 gives us 16, -16 gives us neutral. So this is how we can get to overall neutral for that compound being neutral if we wanted to do this with the formula given instead of separating out the perchlorate ion. And so +7, 2 chlorines, +7 for each. So the oxidation number of chlorine would be +7. So we can do it 2 ways. We can look at the entire formula, or we can break ClO4 minus into its own ion and just work out the charges accordingly. And again, we already did this one, but -1 for the Fs are where we start, -3, and so that's how we deduce +3 for chlorine and something like ClF3. Okay, so now where we can use this is identifying oxidation and reduction. We already did the H2O2 reaction, so again, neutral here by rule +1 -2, and we're just picking out that hydrogen is losing electrons. Now people usually remember either oil rig or Leo the lion goes grr. And so Leo the lion, so like losing electrons oxidation, so losing electrons is oxidation. Hydrogen lost electrons to get to a +1, and so hydrogen's oxidized. Like too early to spell that word. And then oxygen to a -2 is gaining electrons. Gaining electrons is reduction. And so gaining electrons is reduction, oxygen is reduced. And then oil rig was oxidation is losing and reduction is gaining. So monikers help, I think, when 2 terms are just kind of, one of them is the one, the other is the other, to keep them straight. Having some way to remember oxidation is losing electrons and reduction is gaining electrons is helpful. Now, sometimes we get a little bit cute with this, and we define H2 and O2 to be an agent of either oxidation or reduction. And H2 in this reaction can actually be defined as the reducing agent, and O2 is the opposite, the oxidizing agent. And at first glance, I just lost everybody in the room on why we would do this. Now, the facilitator of the reduction has to be oxidized. So the thing that is oxidized, we can call the substance that contains that atom the agent of the reduction of the other thing. And then O2 is being reduced, and it facilitated the oxidation of the other atom in the reaction. So O2 can be defined as an oxidizing agent, or an oxidizer, sometimes it's called. And so I think these words are useful because you'll see them. And it's also then, I think, useful to remember that anytime you see the word agent or a facilitator, usually doesn't mean it's the thing, right? So like if you think of somebody who's an agent for movie stars or for sports stars, are those agents usually movie stars or superstar athletes at the time? No, maybe after they're done playing, they become like a sports agent, like I think Michael Jordan, did he do that? I don't know. Maybe LeBron has an agent company, I don't know. But usually you don't think of people being an agent at the time they're the thing. So an agent facilitates somebody else or something else to do the thing that it's facilitating. So H2 itself is oxidized to allow the reduction of something else. So it's called a reducing agent. And then oxygen here, the oxidizing agent. Now, in terms of semantics, you usually see the atom as being determined if it undergoes oxidation or reduction. So at the atom level, we're usually tracking oxidation and reduction. And usually then you go back to the thing in the reaction, the actual substance that contains the atom as being the oxidizing or reducing agent. So we might say the H atom is oxidized, but H2 serves as the reducing agent, and then oxygen atom is reduced in this reaction, and then O2 serves as the oxidizing agent. Let's look at this reaction here. In the next one, lead plus nitric acid goes to lead nitrate and H2. So lead 0, HNO3 minus, like the NO3 is a minus. In fact, I'm not even going to work out the N and the O here because nitrate stays a minus. The N and the O and nitrate aren't changing, but what's changing is lead is going to lead 2 plus, and then hydrogen plus is going to 0. And so hydrogen plus to 0, lead 0 to lead 2 plus. So did lead undergo oxidation or reduction? Was lead oxidized or reduced? Lead lost electrons. Losing electrons is oxidation, so lead is oxidized. And then the H here is going from plus to 0. It's gaining electrons. So hydrogen in this reaction, the H atom, is undergoing reduction. And it's reduced. And so lead solid would be the reducing agent. And then HNO3 would be the oxidizing agent. So nitric acid facilitated the reduction of something else. That's why HNO3 facilitated the oxidation of lead. Therefore, that's why it's called the oxidizing agent. And then the last reaction, copper plus nitric acid, goes to no reaction. Well, if there's no reaction, there's no reaction. So nothing's oxidized or reduced. So if there's no reaction taking place, if you're told copper didn't actually do anything, like lead dissolved in the acid solution, but copper didn't, and copper would not have been oxidized in that solution or reacted at all, so there's no change, no redox reaction taking place. So you actually have to have a reaction take place in order to classify the change in oxidation state. I like the sound of packing up. Let's actually start class with that example. Let me also point forward. There's this thing called an activity series where you can predict if a redox reaction will or will not take place. We're also not going to make you responsible for this. You're going to talk about this enough in lab that I think that will hit the topic good enough. So you can use this type of series to predict if these reactions can occur, like the lead reaction we just looked at, and just know you're not going to be responsible for problems that look like this on midterm 2. So what I'm going to do is I'm actually going to send out a little quiz. It's not going to be required, but just something if you want to do a couple problems that we'll review at the start of next class over chapter 4 before we get into chapter 5. So we'll start with the problem I skipped and a couple problems I'll send an email out to you about that if you want to take a look at those, and we'll review those at the start of class, and then we'll get into chapter 5 on Wednesday. Thanks, guys. Have a great day.